Thank you very much, Andrew, and thank you for the chance to come and to tell this story. I'm going to talk a little bit about self-assembly in aqueous solution, and this is another liquid crystalline story, and it's about the aggregates that form when organic molecules self-assemble in water and then go on to form liquid crystal phases. So just as an introductory slide, a little bit, to explain about phenomena of aggregation in solution. Now, I guess we've already heard a little bit this week, for those of you who are here this week, about the normal thing of amphiphilic molecules which form aggregates in solution, so things like micelles, liposomes, bilayers. And at the molecular level, in much of the chemistry, this tends to be an entropy-driven effect. It's driven by the hydrophobic effect. But there's actually a whole series of systems where a different type of chemical mechanism occurs in driving association. And this is a system I'm going to talk about today. This is the idea of having board-like molecules in solution where we've got aromatic groups which really don't like the water at all. But if chemically we decorate these groups with sulfonates and hydroxide groups and things that like the water, we can actually stabilize structures that will form in aqueous solution, and then you have the possibility of these structures going on to form liquid crystalline phases. So the order here, shown by this little cartoon, is what we expect to be able to see, where we start to form aggregates of various shapes and sizes, and then we have the possibility, as is shown for this molecule here. This is the food dye sunset yellow or edical. You've got the possibility of these aggregates then going on to form, as a function of concentration, different liquid crystalline phases. So one possibility might be for the molecules to come together, and if you get long enough aggregates here, as a function of concentration, you can get the formation of maybe a pneumatic phase. And at much higher concentrations, you get the possibility of other types of phases. So you might get some interactions between these columns. You might get what's called a hexagonal phase. So this is a particularly simple phase diagram for this molecule for edical, sunset yellow. But it gives you an idea of what we might expect to be able to see in solution. So just one more little introduction slide to this thing, because it's been found now and recognized that there's a whole series of different types of molecules that form these rather interesting phases. We've tended to call them chromonic phases, and this sort of aggregate phenomena as chromonic aggregation. And what people have found, it's particularly two classes of molecules. This has been seen particularly. One has been a set of organic dye molecules that have been around for many years, and also a group of drug molecules that people have found that in solution also tend to form these chromonic phases. And these are actually quite interesting. For the dye molecules, it might well be that you're actually interested in these aggregates. Sometimes for drug molecules, this is a real problem. You actually don't want molecules to aggregate in solution because these aggregates tend to be quite sensitive to what you have present. And so if you're trying to make a drug that has a certain solubility, this may well be a bit of a problem. I'll just say one more thing quickly about this slide that I've shown. I've put up around the side various different sorts of structures that people have suggested over the years. And there's all manner of sort of very clever things that people have used to try and explain the experimental results. There's these sort of hollow tube structures. There's these sort of square aggregate things that form, which then go on to form a mesophase like this. There's these unusual brick layer structures that are believed to form originally from a pneumatic and then transform themselves to this other structure. So there's actually all sorts of things that have been suggested. And, well, there's only a few experimentalists in the audience, so I'm going to try and go on and show actually that some of these suggestions may not be right. And we can actually reinterpret some of the experimental results by using simulation. Okay, so I'll just, one slide just to show you a little bit more about motivation. And that is that actually this whole idea of self-assembly in solution is actually quite a nice thing to be able to do, because you have the possibility of growing these sort of organic molecules that give you the possibility of self-assembly in nanowires within solution. And there's all sorts of things you might be interested. You might be interested in the photovoltaics as a possibility. These sort of structures beautifully flow a line. It's very easy to align them and to get nice monodomains. You can also make inorganic-organic hybrids by using the chromonics as a sort of template, and that's a very nice process too. So there's all sorts of possibilities here for solar cells. But you can also do some very nice nanotech things. So you can form, if you can form sort of hollow columns, then you form these sort of nanowires in which you can trap small molecules or water, which kind of gives you a little factory where you can kind of study nano confinement and things like that. So there's all sorts of nice reasons why it would be good to be able to make these sort of things and to understand their organization and make useful predictions using simulation. So that's really a little bit about what this talk's about. So I finished really my introduction. I'm going to show you quite briefly 3 little stories. One is I'm going to show you how I think with atomistic simulation these days we can understand a little bit better the self-assembly process, and we can validate what we see in simulation in terms of explaining some of the data that's seen by experimentalists when they look at these solutions. So that's going to be the first thing I'm going to tell you. I'm then going to show you how, if you change the interaction slightly, you can control the self-assembly process and change the aggregates. I'll also show you that some of the aggregates that people predicted in the past I think are probably not the right explanation. And then finally, I'm going to show you a little bit of coarse-grained modeling, where we're going to have a bit of fun and play with structures with the idea that in the future we might be able to invent new self-assembled nanostructures. So that's the plan really of the talk, and the work has really been done in my group by these 2 postdocs, and there's one slide from Romnick which I'll show you a little bit later on. So first story is a story about self-assembly in this molecule sunset yellow, which is quite a well understood experimental system. I'm going to try and use simulation to predict what we see experimentally and explain some of the experimental data. So our first approach here is going to be an atomistic simulation approach, and so many of you have seen this already. And I'll say a couple of things about this slide as we go through. For the mathematicians, this is the equations that we use, and of course I have to confess that this holds all manner of evils within it. And the manner of evils are in the form of these force constants here that parameterize the interactions between our molecules. And these are actually very important because, as Claudio and others have shown, if you get these wrong or you get these right, you can make a huge difference to what you see. And these are actually extremely important for what we're going to do. So first of all, I will also say that among some of the force fields you saw with Claudio, not all the force fields are perfect, and so you have to do some work yourself very often to understand them. But in some of the things like this, there are, 50, 100, 150 PhDs that have gone into alone to determine some of these parameters relating to this. So there's huge amounts of work to try and make good force fields. They're certainly not perfect, but they are getting better as time goes on. Now, I'll say one thing in particular about what we're going to use. We're going to use some force fields that parameterize for systems in water. They actually work pretty well. They reproduce quite well free energies of moving a molecule into water, which is very important for what we're going to do. Where they're not quite so good is in the form of the electrostatic interactions. So what we've done for all of our systems is that we've used quantum mechanics to reproduce the to produce an electrostatic picture of our molecule, the electrostatic potential around the molecule, and then have fitted that to produce the partial charges to describe the charge interactions within that system. And that's actually very important, because I think if you get a bad representation of charge interactions in water, then really we can't reproduce as well some of the experimental data that I'm going to show you. Okay, so again, just to say a little bit about what we're doing, we're of course solving Newton's equations of motion for this complicated potential. And we're going to do it for very large systems of molecules in water. Typically, we're going to perhaps work for simulation times of up to about 200 or 300 nanoseconds of time. We're also going to work with a variety of system sizes from about 20,000 atoms up to about 250,000 atoms. So we're going to, for some of those systems, look at what's even today is quite large systems. So let me just say a little bit of what we're doing kind of pictorially. So I'm not showing you the water here, but these are some sunset molecule, yellow molecules in solution. The water molecules are removed, the ions are removed. And what we've just done here is take some sunset yellow molecules. We turned off the interactions between them. It's dispersed them in solution. And then we run this little movie. You can see immediately that as the molecules find each other, they start to aggregate. And of course, we can follow this aggregation process through. Over the time scales of 100 or 200 nanoseconds, you can see aggregates forming spontaneously in solution. You can follow the motions of the aggregates, and you can characterize their structure. And of course, you can do this for a range of different concentrations. Here's a sort of typical simulation box, again with the water removed. And you can see these aggregate structures that have started to form. This is an isotropic phase of these aggregates. And there's a whole series of different aggregate sizes in here. And you can see that when you start to push these up to high concentrations, you start to form strings through the system. So we can see all of that happening spontaneously within the computer system. Now, one would like to, of course, validate some of these interactions that go into our force field and to try and characterize what's happening in terms of some of the experimental data. And we have some ways to be able to do that, both in terms of thermodynamics and also in terms of structure. So in solution, one of the things that the chemists are able to do is to look at NMR spectra. If you look at 2D NMR, you're able to pick up couplings that occur through space between molecules that occur in stacks, and you can see how these couplings change as you increase the concentration and aggregates start to grow. And that's what we can actually do also in the simulations. So we can pull out groups of aggregates from our simulations. We can take out monomers and dimers and trimers and quadrumers as things start to grow. And then we can take each of these and put it into a very large electronic structure calculation. We can do a quantum mechanics calculation for this whole big system. And we can calculate out of that the nuclear magnetic shielding for that, done with DFT at a reasonably high level. And of course, because these are all fluxional things, these are all moving about, you need to have literally hundreds of these types of calculation. When you do that, you can actually pull out estimates for the magnetic shielding, and you can compare that with what you see experimentally. So I'll show you that in a second. Just to say one more thing about this slide is you actually get some rather interesting results when you take just two molecules alone and you move them past each other, because as you do that, you actually find that you perturb the proton interactions, the local fields, and so you actually change the magnetic, the shielding as you do that to two molecules. And so you actually have to have quite good averaging of that in order to get reasonable estimates of what's happening experimentally. So we've been able to do that, and we've been able to do it for both for protons and for carbon-13. And this just shows you a series of protons taken from sunset yellow. We've got the proton number here. This is the experiment. And what you can see in the experiment is that as you go to higher concentrations, you actually start to change the chemical shift as these molecules come together, and you get the influence through space on the shielding. And actually, we reproduced that sort of trend reasonably well. We produced the numbers actually quite well, particularly for monomers. As we bring in trimers and dimers, then we actually see the similar sorts of trends. And actually, if you break this down into what's happening in terms of protons, some of these protons actually shift more than others because they're particularly sensitive to the plane of these rings that they find themselves, this ordering of rings. So actually, we can do very well, and we can do this also with carbon-13. Okay, this is a little movie of one of the stacks in solution, and I wanted to just pull out a couple of things from this, because you can see actually that this whole thing is actually rather dynamic in character. And you can pull out at least two rather interesting dynamical processes that's involved. One is the motion of the stack as a whole, and so on the order of nanoseconds this stack will rotate and move about in isotropic solution. You also actually get this rather interesting ordering that's occurring within the stack, and you get these sort of transitions that seem to occur as molecules move around. So I'm just going to say a little bit more about that very briefly, because we've looked in detail as to what's happening in terms of the molecular interactions. And it turns out if you look in detail at these stacks and look at them over time and look at averages of what's happening, the structure that's preferred is what I've shown here, which is rather surprising and probably not what we expected experimentally. So you actually get a preferred structure where you've got two forms of anti-parallel ordering within the stack. So you've got an anti-parallel ordering where the two molecules are sort of like this as you go up the stack. So this is alternating that way as you go from up the stack like that. But you also get, in doing that, this anti-parallel ordering of dipoles. So you've got dipoles here on odd number on these numbers here pointing out, and then these numbers are actually pointing in. So you've got two interesting forms of anti-parallel ordering that you see within that. But it is dynamic, and if you look at the time evolution of both the stacking distance and of a small stack of 8 here, and then the distance between, you see these rather interesting peaks here that correspond to these dynamic transitions that we saw in that little movie. And what's happening here is rather interesting. So if you look at the stack, there's two different processes involved. One is a sort of out-of-plane translation where molecules can kind of move out of the stack because it's a sort of weak interaction in that direction. And then secondly, you get these rather interesting things that happen in the middle of a stack where it's almost like the stack breathes and moves slightly apart, and as it does that, you get a nice transition where the molecule will flick round. And so you actually see these in real time in the simulation and can characterize what's happening. Now I said also that you can try and match to some of the chemical thermodynamics that you see for in real systems. And we do that by using a non-equilibrium method, Jaroszynski's method, where we try and calculate the reversible work for pulling a molecule from the end of one of our stacks, or indeed pulling our stacks apart. So what we do in practice here is to take our Hamiltonian, and we put in a little spring which links our molecule on the end to our stack, and then we gradually tune up that spring and pull the molecule away from the end of the stack. As you do that, you measure the work for that process, and then you can average that, and that gives you a way of calculating the free energy of association. So we've been able to do that too, and this just gives you a little movie picture to show you what we're doing in practice. So we're taking this molecule here, we're applying this Jaroszynski method, and we're pulling it gradually off the stack over a period of about 5 or 6 nanoseconds in time. Now, in order to do this properly, you need to average over lots and lots of different simulations. So we do this for about 160 separate simulations in order to get a good measure of this free energy change. And if you do that, you get a couple of interesting things out. So first of all, you get the actual magnitude of this, which turns out to be about 7 kT. So this is almost exactly what's predicted by the experiment. So that's the first thing. But you get a couple of other interesting things out. One is that if you do this for dimers and for trimers and for stacks, you find that the free energy change is almost the same if you average over enough separate simulations. And that tells you really that despite the fact that these aggregates are charged, you've got the same free energy for removing a molecule from a stack as you have from, say, a trimer. And that tells you really a couple of things. It tells you that the charges are helping compensate around the stack so that the stacks aren't building up this huge charge on them. It also tells you that you've got an isodesmic association in solution. so that all the predicted isodesmic models that we used originally to explain chromonic association are most probably correct, because you know that the free energy is going to be the same when you add each extra monomer to your system. Okay, I'm going to say just one other quick thing about the structure, and that is that you might have seen in some of the movies these little blue dots moving around. Well, the little blue dots moving around, they were the counter ions, so these were the sodium ions. And because of this free energy result, we know that they're kind of associated in some way with the stacks. And it turns out that the association is very, very weak, that you're constantly getting an exchange of ions from around the stack into the bulk. But there are these preferred places where the ions like to be. One is just associated with the charges at the end of these molecules, but then also linking molecules together. So sometimes you can get this very weak salt bridge that forms, links molecules together, then disappears. Okay, this picture is a little bit of a cheat, because we went on to try and look at the nematic phase itself. And this is roughly what it looks like in terms of what we expect the columns to do. So we've taken some chromonic columns, we've set them up rather randomly, and we've let them equilibrate into this sort of nematic phase. This is the side view, this is the end view of what's happening. You can say that if you look down enough of a column, you can see that these are kind of disordered, that these rotations that go on that we saw earlier in isotropic solution happen here. The system actually is very similar to what we saw in the isotropic phase. It's just very simply that these columns have grown larger, and because of the longerness of the column, we get this transition to a nematic. The reason why this is a slight cheat is that these columns are actually linked up through the periodic boundary conditions of our simulation. So we can do this just by putting a lot of molecules into solution, but when you do that, you actually get columns of all sorts of different lengths, and we're right at really the boundary of being able to do this atomistically. You probably need longer columns than we see, at least in this picture, to get spontaneously aligned nematic phases. So it's a slight cheat. That's just looking down on top and again seeing this overall circular cross-section that was predicted by experiments. Okay, so that's a quick summary of what we've seen, and it shows, I think, that using atomistic simulation you can get a good handle on what's happening in terms of the structure of some of these, and you can get good agreement with what we see experimentally. Okay, so the second and third bits, I'm going to go on and do two other stories. These are going to be much shorter. And the first one of these is using simulations to try and understand and control self-assembly. And the molecule I'm going to work with to start with is a very famous chromonic system. This is one of the very first to show chromonic phases. This is the anti-asthmatic drug Intal 5-DSCG. It has this rather interesting structure. It has a flexible bit in the middle of the molecule with potential for hydrogen bonding, and then it has these two ring structures at either side. And there's been all sorts of competing ideas about how this molecule might self-assemble in solution. This is one of the very early models for Intel. People recognized that something strange was happening when this assembled in solution. They knew it wasn't unimolecular stacks like we have with sunset yellow. And so one of the explanations, we might be getting these hollow square aggregates forming. This was a very recent model by Luke that suggests that these molecules might be forming these sort of long string type things in solution, where we get overlaps here between the rings in a sort of anti-parallel type fashion, stabilized by the presence of these sodium ions at various bits. Now, the reason why this model in particular is being proposed is there's some evidence from NMR that you might be getting some of this anti-parallel ordering between ring structures. So let me show you what we get in a simulation. So this is a simulation of this. This is a reasonably large system of a few 100,000 atoms in size. And I'll just take you through this. So we're stripping out the water here to get towards the aggregates, which we can then go on and analyze the structure of these in solution. So you actually get some interesting results from Intel. And I'll show you by zooming in on what's happening in terms of the aggregates. So what we actually find is that we do get the same sort of generic type of aggregation that you see in sunset yellow. Molecules stack on top of each other. But the structure of the molecule gives you this possibility of having branch states. So we've got a second branch here and a branch here that's where this stack here splits off into two. And we think this sort of behavior here, this is what explains the unusual NMR results that we've seen in experiments. It also explains the rather unusual phase behavior that you get for Intel, which very rapidly forms liquid crystal phases at really quite low concentrations in solution. So it doesn't really support any of these older models for what's happening, but it does show that you have the potential to do quite complicated things in terms of forming aggregates in solution. And just to show you one more thing on this class of molecules, if you do the very subtle chemical thing and change the bonding here as to how these rings go on there, you make another molecule. So let me just flick between those two here. So it's essentially the same atoms just connecting in a different way. I make this slightly more elongated. This actually changes the interactions very, very subtly so that you now get much stronger association. You remove some of the frustration that we saw in Intel. And this actually now gives you a much stronger association in aqueous solution. But as a result of that, this doesn't form liquid crystals. If you put enough of this in, this actually falls out of solution as a crystal. So the message there is that there's some really, really subtle molecular interactions that control this form of chromonic self-assembly. This is one more quick example. This is showing the triphenylene. This is rather similar to the example that Claudia showed, but this is in solution. And what we've done here is put polyethylene chains around a triphenylene core. And what happens here is rather interesting. These molecules will stack, and there's a very strong stacking of about 16 kT when you put these molecules on top of each other. If you elongate the core very slightly, you now change the structure of the columns. You've actually got 3 different modes of molecules coming together within a column. But if you elongate the core even further, then this frustrates the whole column. And these no longer form columns at all. These form kind of pseudo-misols in solution. So again, you get rid of all the chromonic liquid crystal phases just by very subtle changes in molecular interactions. And one final example, this is the anionic dye B1590. Again, this was one of these that we thought experimentally to form these hollow columns. Here's a cartoon of the experimentalist's picture of what's happening. It matches very nicely the X-ray picture in terms of the experimental cross-section of the columns. But again, we don't get this sort of thing at all in solution. We actually get this rather interesting anti-parallel association. But when you look down again on the end of one of these columns, you actually find that it matches quite nicely the experimental cross-section. So we think this is another explanation, and in fact things like this hollow columns are not seen at all in many of the things that people have predicted. Andrew, how long have I got? Just
40, maybe possibly. You've got another 25 minutes or so, 20 minutes.
Okay, I don't need that long. 10 minutes or so. Okay, so final bit of the talk is just to have a little bit of fun, really, with coarse grain models, because what we would quite like to do is to have, now that we can see different aggregates forming in solution, if we can capture the generic behavior within the form of a coarse grain model, this gives us a useful tool for being able to go on to predict mesophases. Now, the reason why we need to do this sort of thing is that you get the rather interesting possibility that when you get the possibilities of different sorts of aggregates forming in solution, you get the possibility you might get coupling between the form of the aggregate in terms of the local stacking structure and then the mesophases that could potentially form from that. And it may well be that certain aggregates will favour certain types of mesophases. And so to be able to really understand that, you've got to be able to throw in literally thousands of molecules, and to be able to do it atomistically is going to be difficult. So we'd like coarse-grained models that's going to allow us to be able to do that. So if we could do that, this gives us lots of possibilities, because it gives us the possibilities of taking things like our disks, decorating them with various functionality, and then being able to tune at a kind of simulation level the kind of structures that we would like to see in nano self-assembly. So the sort of cartoon picture is this, where we use the chemistry to tune the local interactions, and then the aggregates will go on to self-assemble to give us some nice self-assembled structures. So, as a kind of take on coarse-grained simulations, we've had a lot of coarse-grained simulations this week, and we've moved across, of course, the length and timescales as you do that. My sort of picture of what's happening here in terms of this particular talk is that the atomistic model is a little bit like the sort of water pistol picture. So you have, not a lot of power, but you have high accuracy. Of course, if you want to go up to quite longer timescales, then you can actually move to slightly more coarse-grained picture. And we actually do have models, I'll show you, that are moving to this sort of regime. If you want to go to really long time and length scales, as we've perhaps seen this week, you've got to move to a lot more coarse-grained model. And this gives you the power to move out to much, much larger time and length scales. So in terms of chromonic modeling, as with a lot of liquid crystal modeling, there's models that really fit all of these regimes. So the atomistic regime down here, the kind of mid-regime where you coarse-grain out the water, and you leave maybe coarse-grained models of the sort that we saw with Claudio's lovely talk earlier. And then right at this other end, even simpler models where we move to real blob models where we get rid of much of the molecular structure altogether. Now actually we've got projects across all this range of scales. I've just got time really to talk right at this high end today, where I'm going to show you what we can do with some really very coarse-grained models of chromonic systems. Okay, so the introduction to this last part then is just to explain some of the advantages and disadvantages with coarse-grained models of the sort I'm going to show you. And the analogy really is in terms of the exploration of phase space. So if you can imagine that we have this chap here whose job it is to explore this muddy field. His muddy field is phase space that we need to go through in terms of simulation. And what we can imagine coarse-grained models allow us to do is to make this phase space a little bit sloppier so that we can kind of move through it more easily. And so as phase space becomes simpler, then we can explore more of it more quickly. Of course, what eventually happens is that if you make it too sloppy, we perhaps lose some of the physics, and you end up with this sort of result here. So we're going to try to give you some coarse-grained modeling which doesn't result in this, but hopefully just allows us to move through space a little bit easier. So we're going to show a dissipative particle dynamics simulation approach to help us try and understand chromonic liquid crystals. Now this is very similar to the sorts of approaches that people have used for normal amphiphiles previously, but I'm going to apply them to chromonic liquid crystals and allow us to try and understand something about the association. So the basic DPD methodology is very simple, and that is that you have, for the forces that act in your system, you have a conservative force between the sites, which is amazingly simple. It's just a repulsive line here. So 1 over R dependence That 1 over R dependence, of course, leaves you with a quadratic dependence of the energy between two sites, so it's very, very simple. And then in addition to that, you have, so this is our conservative force that you have in a simulation. In addition to that, you also have a dissipative and the random forces that go into the DPD. Together that makes the thermostat. And this allows you to have very soft particles that move past each other very, very quickly. But it does allow you, if you do it okay, to connect sites together and have a sort of pseudo-molecular representation of your system, where you can capture some of the interactions between different groups within a system such as a chromonic, where you have different types of molecular interactions within your molecular system. So to do that, we're going to imagine linking together our chromonic system with a series of these sites, interacting through essentially this potential, and with soft springs to link them together to make the structure of the molecule. So our model chromonics are going to look a little bit like this. We're going to be able to change them according to how we're going to play with the chemistry. But I'm just going to show you 2 very, very quick examples. This is the simplest example. This is based on our polyethylene oxide functionalized triphenylene system. So this is the central triphenylene bit, which we model as a sort of hydrocarbon here. We model polyethylene oxide chains, as people have done in the past for lytropic systems. And then we model these with water beads. So these water beads are supposed to represent something like 4 water molecules. And you have purely repulsive potentials, but by changing the interactions between each of these sites in the very similar way that's been done previously for ampliophiles, you're able to change the interactions of these different sites, and allows you to generate models that reproduce amphiophilic molecular self-assembly. And of course, one of the nice tricks with this sort of system is that it gives you the possibility of introducing new beads. So I'm going to show you later just one system where we've added in an extra set of beads, D here, which is to represent fluorinating a couple of our hydrocarbon chains here. So this is roughly what our molecule is based on. We're based on the triphenylene system, polyethylene oxide chains. We have measures, of course, for the interactions of this from the atomistic simulations that allow us to roughly parameterize the energy scales in our systems. This is roughly what the experimental phase diagram looks like. This is a function of concentration. So let me show you some results very quickly. So this is for this DPD model of the triphenylene system. And you can do some rather nice things with this because, of course, you can look at many, many more sites than you can do atomistically. So I think the largest system we've looked at for this is up to about 1 million sites, where we can just throw things into the solution and see all the nice self-assembly behavior that you see with atomistic models, but see it on a much, much bigger scale. So for example, if we do this relatively low concentrations, we get an isotropic phase here formed of aggregates of all sorts of sizes. You can, of course, characterize by a cluster algorithm the stacks, the size of the stacks. You see that as a function of concentration, this line will change. You see this nice exponential decay of stack sizes that we see in the isodesmic model. And so from this also you can extract a free energy from the isodesmic model and use that to parameterize the interaction between the molecules. And at very high concentrations, you get the formation of a nematic phase. Now this is no longer a cheat because we've got these very long stacks here that are formed. You'll see that even within the nematic, there's actually still shorter stacks. Some of these stacks do go all the way through the periodic boundary conditions, but this now forms nicely a nematic phase. And if you take that to really high concentrations, you actually now see that these rods will now start to order. You get hexagonal packing, and we now see the M phase or the hexagonal phase that you saw at the other end of that phase diagram. And just very quickly to show you that you can now play with this type of model, that you have it, you can play with the chemistry. So if we change these to fluorinated groups at the end of this molecule here, you get some rather interesting effects, and this hasn't shown up quite as well as I wanted it to. So you might just be able to see that between stacks here, you've got some little red blobs. So this is just in a melt with no solvent in it. And what's happening here is that you're getting microphase separation between columns here. So we're now getting columns that are starting to be linked together. So you get groups of 3 columns linked together by this microphase separation between these fluorinated groups that don't want to contact with the hydrocarbons or contact with the polyethylene oxides. And if you look at that in solution, you get some rather interesting effects. So as this starts to melt, as you add water to this, you start to keep these 3 columns together. And what you get is a rather interesting thing where these columns start to try and aggregate together. As they do so, they twist. And if I zoom in there, you get a rather interesting effect. So you get these sets of columns which have started to twist together. And out of this system, you start to get chirality just randomly appearing. So I get columns, some of which are right-handed twisted, some of which are left-handed twisted, that occur spontaneously in this achiral system. So we get chirality out of an achiral system just by using these sorts of extra additional interactions. Okay, well, I think I've had my time, so I should just conclude and allow us to all go off for lunch. So I've tried to show you 3 things, really. First of all, that atomistic simulations can give us a nice picture of self-assembly in aqueous solution. If we try very hard with our atomistic models, then we can measure some of the things that we can measure experimentally, and we can use that to validate what we see in the atomistic models. So a lot of work that goes into the parameterization, we need to check this, but in doing so, we do think we're getting a good picture of what's happening in terms of self-assembly. If you do that, you can use the atomistic models to predict the shape and the structure of aggregates that you see. And so this is very useful from the point of view of trying to understand some of the experimental measurements that people have seen in the past. But it's also, I suggest, quite useful in being able to design molecular interactions to allow you to design from the kind of bottom-up aggregates that have kind of useful kind of shapes and things that you would like to design and see and perhaps self-assemble onto surfaces. Then finally, I showed you one of our coarse grain models that we're using to try and have a play with the interactions in these systems at a kind of longer length and time scales. And we think with models like this and some of the other coarse grain models that we're using, it gives us the possibility of playing a little bit more with the chemistry and being able to play with how the chemistry affects some of the phases that we might be able to get out of chromonic systems. And so that brings me to an end. And just to say this work is sponsored by EPSRC, and to thank you all for your attention.
Thank you very much. Again, we've got time for a few questions. Please.
I'm interested in your carrier structures.
Yes.
Did you make by chance the analysis of the mass distribution in the clusters?
I haven't got a mass.
In terms of tensor, of course. In terms of tensor.
No. So
that would give then information what was going on, actually.
Okay, well, that would be interesting to do. So all I can say with the chiral things that we've seen, they just seem to crop up randomly in some of these of these systems. So we've run various chains. For that 2-chain system I saw you is the one that really seems to promote it. We can get columns that are untwisted. We can get columns that are twisted one way, columns that are twisted the other. We haven't really understood what's going on. It seems that columns can start as 3 columns together, and they seem to be able to relax in the simulation. So I'm presuming that they're lowering the free energy by twisting. But we haven't really looked at the mass distribution. We've not really characterized them perhaps as well as we could do.
Any other questions? Please.
Well, are these static? Are these chiral organizations static, or do they change in time during the course of
Everything
the
fluctuates in all the chromonic systems that we see. So in the coarse grain models, just as the atomistic models, the columns are all flexible. So they all wiggle about. The chirality fluctuates a bit, but as I said before, they do tend to relax into this chiral structure. So if you get three columns that form together in solution, they seem to relax and twist. They don't normally get relax the other way, so we don't see them relaxing out of the twisted state. You can do a few things that you can do experimentally with these. Of course, you can shear them in the simulations, and we have done that. So you can even shear things that are near the pneumatic phase transition, and you can put them in these nice moving boundary conditions, and you can shear them, and you can start to form pneumatics. You can apply fields, of course, and you can align them too. So they do seem to work as, you know, just as the atomistic models, but they're all flexible structures.
Any more questions? Please.
Do you think that this isodesmic character is general for all the chromonic systems?
All the things that we've looked at so far, they seem to be isodesmic. Now, it's one of these things that in the literature is kind of confusing. So people make all sorts of measurements, and there's some papers out there, even for sunset yellow, that say, no, it's not isodesmic at all. Whereas other experimental measurements say, yes, it is. And I think one of the reasons is, again, down to how you interpret the experimental results. And some of the predictions are actually based on NMR predictions as to what's going on. And one of the things that we saw in some of our simulations that we did of shielding is that you get, the whole picture that the people get who fit their NMR data to isodesmic or not models, it's a very complicated picture because when you've got small numbers of aggregates, the chemical shifts that you see on the on some of the protons in the center are not the same as you get with protons on the outside of columns. Now, this is never taken into account in some of the fitting that occurs. So people fit these things and then struggle to fit them to isodesmic models, and then, you know, say, oh well, it can't be isodesmic association. So I think some of the experimental information out there is just people not really properly interpreting what's happening experimentally. And also, when you change concentration in some of these systems, you change the free energy of association. So when you have lots of columns, you start to get some columns interacting between them, and you can imagine there's a local dispersion force with smaller aggregates between larger columns. That potentially can also change the aggregation. And again, I think people don't really realise that when they try and fit some of the isodesmic models. So I suspect most things are isodesmic, but some of the experimental work out there perhaps doesn't realise that.
Mark, thank you very much indeed.